Hello, my name is Tyler, and today we are going to be discussing limits as x goes to infinity. But before we get started on that, we are going to have a review of what we already know about limits. And that is that limits, they don't actually have to hit any values. Like, let's say that this equation was x times x plus 3, all of that over x plus 3, and this right here is x equals negative 3. That means that there will be a hole right there, and limits can exist without the actual point existing. All they need is that for the bottom half and the top half, or left and right, and to connect at that one point, it's just not actually hit it. So that allows us to solve for points like that, which is useful. Just hold on. And now let's get back to the subject at hand, which is going to be the limits at infinity, which is what this video is supposed to be explaining. So, like most people know already, you can't just straight up plug in infinity to any equation. It doesn't work, because infinity, it's not really a number, it's more of a concept than a number. So we can't have like infinity to the power of 3, that's not really infinity. Infinity to the power of 3 plus infinity squared. We can't do that. We can't solve for that. But however, the thing is, we can plug in for something as a limit approaches infinity. So we can like say limit as x approaches infinity of x, and then as the x value gets greater and greater, the y value is also going to get greater and greater, and then y is going to equal 100 infinity. So I know that there's one fundamental rule of limits, is that it has to approach it from both sides. And this pretty clearly violates that, because if something goes off into infinity, you can't really have another infinity, like going in the opposite direction beyond the first infinity. That science says no. So, when you write limit as x goes to infinity, when you write that, you are actually meaning to write limit, whoops, no line there. That's limit as x goes to infinity from the left. And when you write limit as x goes to negative infinity, you're writing that as limit as x goes to negative infinity from the right. So, now you might be thinking, like, what even is something as limit approaches infinity? It's a concept, you know? And then that's pretty much a horizontal asymptote, which has probably already been covered. So, horizontal asymptotes, as you know, like we can draw x squared, not x squared, 1 over x. What am I talking about? We can draw that. And then it's as x goes to infinity, the y value, it approaches a certain value, and that is 0, as you can see right here. And it never actually hits it, but however, it approaches it. It's continuing to do that, and that's essentially what limits at infinity are. The values, they approach the number. See, this is going towards infinity, but it never actually reaches it. So now you might be thinking how we actually solve these problems. So let's say that we get a big, ugly number like this, x squared plus 2x, and then x to the, let's say, third again, 3, because why not, 9x squared. I'm like, oh, now we have to find limit as x goes to infinity. We're trying to find the asymptote for that, because we don't want to graph that. That would be painful. And like we can't, let's say if we just try to plug in infinity, it wouldn't work because then we would have infinity to the fourth plus infinity to the third plus 2 infinity, all of that over 3 infinity to the cubed and 9 infinity to the squared. So we can't solve that. So we need to find which one increases at the fastest rate. So like obviously it's going to be x to the fourth. So that's like a cheaty, quick way to solve it. Now the way that you're actually supposed to solve it is by getting rid of all the x's, and well, not getting rid of them, just turning them into smaller, nicer to work with x's. So we'd multiply this entire thing by 1 over this number right here, that one. It's the high number, the x, it's the x to the highest number on the denominator, not the numerator. So then after that, we get 1x cubed, and then that simplifies to 0, so we're not actually changing the value of any of these, we're just changing what it looks like. And then we get x plus 1 over, no, x plus 1 plus 2 over x squared. That's 3 plus 9 over x. And then that, if we plug in limit as x goes to infinity to that we can solve. That's plausible. So if we do that, then we get infinity plus 1 over, well, plus 1 plus 2 over infinity. All of that plus 3 plus, no, over 3 plus 9 over infinity. And then any number divided by infinity, as we've already discussed, that equals 0. So we just, boop, get rid of u, and infinity plus 1, that's pretty much infinity. Infinity over 3, that's pretty much infinity. So then there we go. We got a nice infinity right there. And then let's say that, let's say that we have a denominator that is greater than the numerator. So then we have something like that. So then what do we do in that circumstance? Because we pretty much do the same thing. It's we divide it by we divide it by the same thing, and when we do take that number 1 over x to the fourth, 1 over x to the fourth, and then we get 1 plus 3. That doesn't matter. I don't have to write that out. You guys know that's 0. 1 plus 0. I started on the denominator because I don't know why. And then that's 0 because it's x to the fourth. And then that's also 0. So then we get 0 over 1. And then that equals a beautiful 0. And that's all you need to know. That's all, folks. Tip of the hat. Good day.